Vectors. Starting off with some vocabulary. Magnitude. What you should know about magnitude is that it just means absolute value. It tells you how big or how much some quantity is. Scalar is a mathematical term for a quantity that has only magnitude. So only a quantity that tells you how big or how much of something. No direction. Meanwhile, a vector is a quantity that has both magnitude and direction. Oh yeah. Finally, components. These are two numbers, one called a horizontal and one called a vertical component, that describe how far right or left a vector goes and how far up or down a vector goes. More about all of that to come. So what is a vector? Any quantity that has magnitude and direction. Magnitude is the absolute value. Direction is where that quantity points. In physics, we will study a bunch of different vector quantities. This is in past tense because in previous years I had this in a different order. Some examples of vector quantities are displacement, velocity, acceleration, and force. We also have momentum. These vector quantities are always going to be represented with a magnitude and a direction. Scalar only has magnitude, not direction, so like temperature, time, distance, speed, mass, energy. We represent a vector with an arrow, and these arrows have a length to them. That length represents the magnitude. So whenever drawing a vector arrow, it's important to represent the magnitude with a proportional length. Big vector means there's a big magnitude. Small vector, small magnitude. We represent the names of vectors with the capital letter, or lowercase letter, I guess, could be, and then this little arrow over top of the letter. That just tells you that we're dealing with a vector here, not a scalar. Whenever you're reading, it's important to have the vector notation there. However, as we go through the year, you're going to recognize what is a vector and what isn't a vector just by knowing the definitions. If we're talking about a force, we know that force is a vector, so obviously we're going to treat it like a vector. Here we can see vectors A and D have the same magnitude, same length, and the same direction. So these two vectors are equal. Here we're looking at a circular grid. Vectors A and C have the same magnitude, which is 10. It goes all the way out to the 10th ring. And then vector B goes to the 8th ring, so it has a magnitude of 8. The direction is described by the angle a vector makes with the positive x direction. Vector A is pointing somewhere between 45 and 60 degrees relative to the positive x-axis. Positive directions above the x-axis and negative directions below the x-axis. Positive directions to the right of the x-axis and negative directions to the left of the x-axis. Vector A has a direction of about 53 degrees, and vector B has a direction of negative 150 degrees. That negative is important because it tells us exactly what direction we're pointing. Vector C has a direction of 135 degrees. This is a math thing. The physics piece of this, we're usually going to represent direction of vectors with a positive or a negative. We'll define our coordinate system to say up is positive, down is negative, or sometimes we'll say down is negative and up is positive. And then we'll just use the directions accordingly, and we'll use that negative to represent opposite of positive. Vectors can also have components, which are pieces. These pieces, we can look at vector A. Vector A has a 1, 2, 3, 4, 5, 6 boxes to the right, and 1, 2, 3, 4, 5, 6, 7, 8 boxes up. So we would say the horizontal component of vector A, or A in the x direction, is 6 units, and the y component of vector A is going to be 8 units. From this information, we can figure out the total magnitude of vector A. Can you see how? It's going to be the square root of A in the x direction plus A in the y direction. You might know this as Pythagorean theorem, and that's what we're dealing with, is just triangles. In physics, we love to make right triangles. It makes our lives easier because we can deal with them in very simplistic ways like this. Vector B's components are 7 to the left and 4 down, so the B components are -7 and -4. Another way that you could represent these vectors is if we'll look at vector B, and we'll use the x component, -7, and the y component, -4. There may be different notation that you'll come across, particularly if you're in AP Physics C, and that is unit vector notation. For unit vectors, well, let's just take regular vectors. We normally talk about x, y, and z if we are talking about three-dimensional things. Well, instead of x, what we can do is multiply a unit vector, which has a quantity of 1, in the respective axis. So rather than saying x, we would say I hat, and instead of saying y, we would say j hat, and instead of saying z, we would say k hat. You can remember this because they are in alphabetical order, I hat, j hat, k hat. So if 7 represents our x and -4 represents our y, we would write this as -7 I hat, comma, -4 j hat. And we'll talk about how to deal with that later on and how to combine vectors using this unit vector notation. AP Physics 1 students, though, don't worry about that. And then vector C is -7, +7. You can express the magnitude and direction just like this, where we have 10 at +53 degrees, which tells you that vector A is pointed at 53 degrees above the positive x-axis. You can also represent this with our x and y, or horizontal and vertical components. There's going to be times where we need to change a vector from the total combined vector into its pieces, into the horizontal component and the vertical component. To do this, we're going to deal with a right triangle. So we're just solving right triangles. The direction of vector A is going to be given to us as theta sub A. Theta is the Greek letter. We often use it to represent angles in physics. The components of vector A are A sub x and A sub y. Makes a right triangle. Yes. Yes. Because A in the x direction is touching this angle, we would say this is our adjacent side. Adjacent just means touching. And then A in the y is way over there. This is our opposite side. And of course, the really big long one is our hypotenuse. This comes in handy when we have to figure out what is our x component, or what is the y component, or what is the angle. To do that, we're going to look to our trigonometry knowledge. Quick review. We have SOHCAHTOA. TOA. Taking sine, the SO, we would write this. I sometimes see students say sine is opposite over hypotenuse, and maybe in math class this works. In physics class, this is going to lead to confusion. There's missing pieces here. First of all, there's a theta in there. Sine of our angle, because sine is a function and theta is going to be the input of that function, equals opposite over hypotenuse. That's important if particularly we needed to solve for theta. But for right now, let's say we needed to solve for our vertical component here, a sub y. We're going to multiply hypotenuse to each side, so that way hypotenuse goes away from here. And what we're left over with is the hypotenuse. Ooh, sorry about this writing. This pen is not great. Hypotenuse times sine theta equals opposite. Just like in math class. Nothing new here, I hope. If it is new, then grab this new skill and really enjoy it. This can be broadened to represent all vectors. If we wanted to find a vector in the y direction or the vertical direction, we could broadly say we're going to use the formula, the magnitude, which is our hypotenuse, times sine. Uh-oh, I don't know what's happening. So that will give us our y component. And then in this case, it is a sub y. In the x direction, we can do the magnitude, which is our hypotenuse again, times cosine, because the horizontal component in this case is touching our angle, and touching means adjacent. Boy, this pen is just awful. I am so sorry about this, everybody. Okay, that's the really long, drawn-out piece to it. Again, Pythagorean theorem can come in. Let's say we needed to solve for the angle, and we were looking at tan theta. We had our y component and we had our x component. Back to this terrific pen. Now that we have our formula, tan theta equals y over x, or opposite over adjacent, if we want to solve for theta, we have to take the inverse of this tan function. And if we do it to one side, we have to do it to the next side. This is not dividing by tangent, because it's a function and there's more to it, but you know. So what we're going to end up with is, I can just, theta equals the inverse tangent, or arctangent, y over x. Heads up, you will get the exact wrong angle if a in the x direction is negative. So if a in the x direction is negative, you have to add or subtract 180 degrees to the direction given to you by the inverse tangent. You'll get a better feel for this as you do it more in class and in context. So here's an example. Change a equals 8 at 60 degrees to components. It's drawn for you. Pause the video. It's on the square grid as well. Pause the video, try it for yourself. Done? Good. Hopefully we got 4 and negative 6.93, or negative 7. Now change b equals 5 at 143 degrees to components. Pause the video, try it for yourself. Here comes the answers. Negative 4, positive 3. Do this on your calculator. Don't just count the boxes. That's not real interesting. think this is the last one. Here's an example where we needed to do something with that 180 degrees because we get the negative angle. So we're going to add or subtract. Here we're going to add to get the correct direction, which is 148 degrees.